Okay, so let's start. We are talking about like more special graphs, especially sparse graphs in general, planar graph, bounded genus graph, H-minor free graphs, and bounded arboricity graphs. These are important set of sparse graphs. Other class could be expanders, essentially. But these are like two important things. Now we have this idea that we want to do. Okay. So we want to do graph decomposition. So we discussed previous time. I mean, how can we solve some problems based on separator decomposition? What was the idea? The idea is that we want to find on this graph if we can find separator, which are small, and the small generally means n. If the n is the number of vertices, you want to get a square root of n. Or if k is the size of parameter, you want to get a square root of k. Something sublinear, as long as the sublinear is actually good. You will cut these guys, and then you have some smaller piece, and then on each of them recursively, you will do that. Generally, the idea is that those separators, you can just put them essentially on the trash, or you can ignore them. And then when you have some components which are small. Then on these components, you have a different definition of a small. If you are just considering for some kind of maximization problem or like maximum independence, etc., it means that the size should be a small. And a small means up to log n, essentially. But for other one, like for other bidimensional parameters, these are minimization problems. When we say that they are small, it means that in terms of size of the parameter should be small. So, for example, the k should be less than, I don't know, log n or something like this. Yeah. So the size of the parameter should be small, because if the size of the parameter is small, the running time of this fixed parameter algorithm would be 2 to the k times n, say. And if k is log n, we can solve them in polynomial time. So we will cut them until at the end, each of these, so these are all these separator things, such that we will get some things here, and then we will generally ignore all of them. We will put them in trash, and because their size is linear, is sublinear, each of them, we can, the same way that we have bounded previous time, actually, I think it was here that we bounded them. It is in the slide. So you can always bound them and say that number of separators are not, like the total number of vertices in the separator is not a big deal. And then, as I mentioned, on each of these guys, because the size of the parameter is small, because there's a fixed parameter algorithm for the problem that we are considering, we can solve these problems. If there is no fixed parameter algorithm, then we need to go until the size of them becomes small. Not just the size of the parameter becomes small. And then we solve the problems. So again, a separator was a set of vertices that when we remove them, then, so this is a separator is a set of vertices that when we remove them, then essentially you can have two components. You can have more than that, but you can always put it in two components, essentially, such that the size of each of them is at most 2/3 and is at most 1/3 of them. So when we remove this separator, so when we remove the separator, the size of them should be between 1/3 and 2/3, and essentially any components.
Like connected components?
Any connected components.
Okay. So the graph becomes disconnected.
It should become disconnected, yes. Each connected component should be that. And the idea that when you remove it, then you can solve each of them. And why 2/3 was important, because if we discussed before here, this one, the depth of the recursion would be this. That is very important. Otherwise, the depth of recursion would be n and so that was essentially about the separator decomposition that we discussed. Though we try to find a small separator, again, a small means sublinear in n or k. K is the size of parameter for, say, for minimization, which is important. then you will reach some pieces which are either small, for example, independent set, or their size of the parameter should be small. And as I mentioned, this is essentially Lipton-Tarjan approach that we discussed. So this is originally, this is the approach by Lipton and Tarjan that they have used it for maximum independence set, but we generalize through bidimensionality for lots of other parts. There is another one, it is called simplifying decomposition. So this is the originally, it is Lipton and Tarjan. This one essentially originally is Baker. So here we try to, this is 83. And then there is a paper by, Baker has used this one for planar graphs in 1983. Then around 10, 11 years later, Aurora used the same approach for plane graph. And again, planar graph is the graph that you can draw in the plane without any crossing of the edges. Plane graph is the one that you can, like, for example, draw them in two-dimensional plane, R2 essentially. You just the points there and the edges would be there. Interestingly, he didn't refer to Baker, but actually this was based on Baker, the approach that he took. So that is Sanjay Barrow. But here, what is the idea? The idea that we try to heal this graph that we have, they have large intersection with each other, but these are simple graphs essentially, or simple pieces. And generally we mean bounded treewidths. So this is also very general set of theorems. These are like the hammers. To get each of them, you need to do lots of case analysis. But when you have it, then you can use it very interestingly. So, so the first theorem is this one. Any odd H-minor free graph, odd H-minor free graphs, these are like a generalization of H-minor free graphs, essentially. Like, I don't want to go, the definition is a bit more technical, but you can just define, C and do that, but it's a bit more general than H-minor. So odd H-minor free graphs can have their vertices or edges partitioned into two pieces such that each induced graph has bounded treewidths. Good. So here, again, odd H-minor free graph is a bit more general than H-minor free graphs, but this includes H-minor free graphs as well. Their vertices or edges can be partitioned into two pieces such that each induced graph has bounded treewidths. As I mentioned, this was known before for planar graphs, then it was for apex minor free graphs, and then was for H minor free graphs. This was this work that we had it, and there was other work in parallel. And this one is more general, which is for odd H minor free graphs. By the way, apex minor free graph you will hear. What is the apex graph? So apex minor free graph is so this is the apex. So you have a planar graph, and then you will add one vertex, and then you will add it to some vertices in this planar graph. This vertex is called apex, and this is called apex graph. So apex minor free graph generally means that a graph that does not have this kind of apex graph. Can consider more canonical case that you have a square root of n by a square root of n vertex. Grid actually, as I mentioned, planar graphs are essentially represented by grid, and then you add one vertex and you will add it every single time. This is, you can say canonical apex graph. But so apex minor free graphs are the graphs that they don't have this graph as the apex, essentially. This graph as a minor, this apex graph as a minor. So what is the theorem that we have? See that the vertices can be essentially colored by two vertices. So here, essentially, that you can just partition into two sides such that each of them have bounded treewidths. So here, for example, this is one set and the other one is other set. So what is the benefit of this theorem? Just say, I mean, this like it's like so powerful. And let's talk about the chromatic or coloring number of a graph. So you want to use the fewest number of colors to color the vertices of a graph such that no two vertices which are connected by an edge have the same color. So this is a coloring problem. You want to find the minimum number of colors that you can color the number of vertices, that you can color all the vertices such that no two vertices that they are essentially adjacent have the same color. This is a classic NP-hard problem, and it is inapproximable within a factor n to the 1 minus epsilon. Unless ZPP essentially is, some kind of, some generalizations of P essentially is equal to NP. So essentially, there is, under this complexity assumption, there is no n to the epsilon. So essentially, what's the meaning of that? Not better than n to the minus epsilon. It means that, like, if this graph is given to you, you just color each vertex with a different color. So then you have n vertices, and you are not very far from the best thing that you can get in mononomial. So these results give the first two approximation for chromatic number of odd H minor free graphs and of course H minor free graphs. Again, the problem is very hard, but we can solve it easily using this theorem. Why? You just partition into two sets. Then each of them is the induced subgraph. Induced subgraph has all the edges there. And it is a bounded Treewidth. As I mentioned, in bounded Treewidth graphs, almost all problems can be solved in polynomial. So you will essentially find the best coloring of this bounded Treewidth graph, like essentially the blue one and red one. Good. Find the best coloring of them. In polynomial time, you can do that. Essentially, the dynamic programming, which is generalization of dynamic programming on trees. Then, how can you get a two approximation? That would be easy. So you said that here you are using the colors 1 to, I don't know, K, or the blue one. Here you are using the color 1 to H. Then you will, but the issue is that there are some edges in between. So, but first you know that, like essentially the coloring, like the chromatic number, the chromatic number is actually greater than max of K and H, correct? Because these are, both of them are induced subgraphs of the graph. Because they are induced subgraphs, so you can find the optimum solution for them. So you know that the chromatic number of the whole graph would be greater than max K of H. What is the one that we can get it? We can get K plus H. Why? Because the first guy, you are just using 1 to K. For this guy, then use it K plus 1 to K plus H. So these are the colors that you are using. So color k plus 1 plus color k plus h. And you can always say that k plus h is less than or equal to 2 times max of k over h, correct? Because always this maximum would be greater than that. And of course, this is less than 2 times chromatic number of the graph. So it means that the OR algorithm is using 2 times the chromatic number of the things. So we get a 2 approximation for this problem. Good. So this is a 2 approximation for the chromatic number, which is a very hard problem, but on H-minor free graphs or all the H-minor free graphs which are a bit general, more general than that, then we can actually solve them, get a 2 approximation. Yeah.
So if you solve for like the impact.
Yes. And this is essentially the general idea. So you can say that in bounded Treewidth graph, I mean, you can represent them by some kind of dynamic programming. There are 4 type of nodes that you will have it for things. You have some kind of a start node, you have an end node, you have a join node. There was one other types. But in general, because it is a bounded Treewidth, the whole idea is that you can represent it as a tree. This is a tree decomposition, such that on each of these nodes, there are only bounded number of vertices. So I don't know, maybe there is, say, Q number of vertices. Then all possibilities of this one, you can essentially have it. So if you want to do it the minimum number of colors, essentially, then you can have all possibilities of this Q persons, essentially. And that would be essentially polynomial still, because it's bounded things. But these are non-trivial algorithms for bounded Treewidth. So you need to essentially work on it to know that. But there are lots of theories about bounded Treewidth graphs. So these are like some of them that say that even this is some kind of logic that you can, the people have considered it so much that, for example, if your problem, you can represent it that monadic second order logic, then you can get it solved. And the logic is essentially some kind of language. If you can write your problem in this language, then we know that you can solve it in full log. So you can read more about it, is beyond this, but this is the idea that almost all problems, except some problems, there are like some kind of graph isomorphism or something, some versions of that still you cannot solve it in even on trees. On trees, I will say even, and as well as bounded Treewidth graph. But the rest of the problem almost you can solve in session. So this is the one that you can actually solve it and get the exact thing. But this is the idea. This is like it's a hammer essentially. For this graph, whenever you have it, you can get actually use these theorems and get it. If you want to get it, I mean, like from the scratch, it's very messy and lots of case analysis, etc. But these theorems helps you a lot to get the result. Now, this is a generalization for H-minor free graphs, which is important. So here we could get 2 coloring, 2 approximation, and 2 actually we cannot get better than 2 approximation for this coloring, because I mean, at least using this approach, we cannot get anything better than 2. However, there is a generalization that can be used to get PTASs. Now, this is somehow similar to those type of PTASs that we had it for using generalization of Lipton-Tarjan through bidimensionality. He said that any H-minor free graph can have their vertices or edges partitioned into k pieces, such that deleting any one piece results in a bounded Treewidth. And again, this is important. You can, this version that I have mentioned Sometimes the edge version is important, sometimes the vertex version. So and this is interesting, so that it can be, so in the previous case also was like this. This one that we had it here. Here also we had it the vertices or edges. Notably, this is the vertex case that we used, correct? But sometimes you may want to use edge case, that the edges can be partitioned. So in that case, actually you have two graphs that just the edges. So you have some edges in this graph or some edges in the other graph on the same vertex. And each of them has bounded trees. So here we use the vertex version, but sometimes the edge version is used, that we will talk about. And one other thing, interesting thing, so this separator theorem, I mean, that we discussed, so generally they are not the best, the Lipton and Tarjan type of thing, or by those through the separator, they are not the best to handle weights. For weights, they may suffer. These approaches are much better for weights, and they can actually handle weights as well. There's some generalization of weighted separators and others which are very complicated, but using this, you can actually get it much easier. Yes, so this is the example that I have mentioned. So this is like so this is the graph. Then, I mean, that was the idea. That so you have these two graphs, you will essentially color each of them, and then when you put these vertices together, then you can shift this one by K, and then you get the thing for the whole graph. Okay, so what does this theorem say? This is a generalization of previous. It says that for any H-free graph, you can have their vertices or edges partitioned into K pieces such that deleting any one piece results in a bounded previous graph. So if you put K equal to 2, would be the previous case, because you can partition into 2 such that if you delete any of them, the other graph has bounded trees. Here it says that you can partition into K pieces such that if you delete any of them, so you can essentially partition into these K pieces, such that if you consider any K minus 1 of them, it has a bounded tree. This theorem is not correct for odd binary free graph. So we cannot, for odd binary free graph, we cannot create this one. The 2 was the best for odd binary free graph. But for H binary free graphs, you can get this result. So this result works for H binary free graph, but not all the H binary free graph. And one of the main applications actually is for this problem is for max cut. So max cut, in general, it has a simple 2 approximation. I think we discussed in this class. What is the max cut? You want to partition the set of vertices. Let me see whether I have mentioned it here or slide do I have. Good. So let me mention this one, for example, for max cut. Good. So let me see whether I think that should be good. Yeah. So what is for the max cut? So the max cut is that you want to, the graph is given, you want to partition the set of vertices into essentially V1 and V2 such that you will maximize the number of vertices in between and number of edges in between. Good. And this is called the max cut. You can get a simple 2 approximation for this problem, just putting each vertex with probability 1/2 V1, 1/2 V2. Then you can say that each edge essentially appears in the middle with probability essentially half. So we get half of the set of edges. So this is a very simple half approximation. And there is something you can, using that semi-definite programming, you can actually get something like, I think, 0.8 something essentially. But this problem is APX hard. What's the meaning of apex hard? Apex hard means that there is no 1 plus epsilon approximation. There is no PTAS. So apex hard essentially versus PTAS. The problem is apex hard. We know that you cannot get 1 plus epsilon for arbitrarily small epsilon. Versus PTAS that we say that we can get 1 plus epsilon for arbitrarily small epsilon. Constant. So this is versus this. So this problem is general apex hard. But on H minor free graphs, you can actually get a PTAS force. How can we get it? So consider the whole graph, use this theorem. So generally, this is the case. K would be 1 over epsilon. So you want to get a PTAS epsilon. You will put K in the order of 1 plus epsilon. Good. Partition this graph into cases. Good. Now, if you partition into cases, you know that this max cut in at least one of these sets that you have. So here we are using edge version. Previous time for coloring, we use vertex version. Here we are considering edge version. We know that in one of these K things that I have, K sets that I have, and these are edge sets, K edge set. So in one of these K edge sets, optimum has at most, like essentially, say, I will say, just let me here. In one of K sets, I have at most 1 over K of opt. Good. So this is, we are partitioning the whole edge set. Partition means that each edge, we are using the edge set here, not the vertex set. Yes, vertex set is not useful here. For coloring, vertex set was important. Edge set is not useful because you couldn't do this interleave thing that we are doing. But here we need to use the edge set. You will partition the edge set into K parts. Then we know that, what do we know? We know that like one of these sets has at most 1 over K of opt. Good. We don't know which one. We can guess that one. What's the meaning of guess? We can try all possibilities. We have these cases. So we will remove this one so that this is not. Then this graph becomes bounded Treewidth graph. On bounded Treewidth graph, you can solve max cut in polynomial. Good. Then in this graph, you will get essentially, so how much we are losing essentially? Because when you solve it on this ground, you will get it optimally. You will partition essentially to these things. From these things that you essentially forget, you may lose at most 1K of opt. And so 1K would be, so it means that essentially 1 over K would be epsilon. So this is epsilon opt. Good. So just now you don't know from which one, but you will try each of them. You will get, and here we say that any of them, if you delete as a bounded Treewidth. So you will consider the first one, you will delete it. The rest has a bounded Treewidth. So you will solve the problem on that one and find essentially a max cut there. Then you will solve, remove the other one and then solve the max cut there. Second one. And you take just the maximum. Again, this is a very natural and interesting algorithm, and even getting these things are not that hard for, at least for planar graphs or bounded genus graphs. I will mention how you can get these things essentially come from some kind of PFS. So that's the thing that you will get it, and then you can solve for max cut. You can get a PTAS. It was not known before our paper actually that we mentioned. And if I'm right, I think a max cut, you can solve it exactly, I think, on planar graph. But on H-minor free graphs, I think the PTAS is the best. That you can check it, but I think that's. But yeah, so max cut, you will use the edge version and you can get actually the problem solved. Good. So far there are two versions. This is about the deletion versions. Some problems now they need actually the, this is the whole thing. We talk about in bidimensionality. This graph miner considers deletions and essentially like deletion and contraction. But in bidimensionality, we will focus more on contraction part. As I mentioned, contraction part generally considered from the dominating set, for example, problem, which is a set cover problem, which is a more like a computer science type of problem. So the same thing here. So as we mentioned, so there are problems which are close under contractions, but not minor. So in particular, these are like someone said, dominating set that we talked before, connected dominating set, face cover, maximal matching, and traveling salesman, TSP problem. We will talk about this one as well. So this is the theorem that we had it, essentially, that was stuck 2011. These are, like, as I mentioned, these are the hammer theorems. We said that any H-minor free graph can have their edges partitioned into K pieces, such that contracting any one piece results in a bounded treewidth. Good. So what is the thing? So that we can partition into K sets, that if you delete this set, then delete vertex set, or in the edge set, we said that, okay, you will partition into edges into K sets, such that if you delete any edge set, then it has a bounded treewidth. Here we said that if you contract this set of things, then it has a bounded treewidth. So essentially it means this one. For example, if you contract this guy, then the rest, it has a bounded treewidth. So there is a polynomial time algorithm. Before this was known for planar graphs and bounded genus graphs. The planar graphs, that was Klein approach. And then this bounded genus graph that we had it, and then we had apex minor free graph that in this paper, and then this was for H minor free graph, which is on Stuck 2011. So this was a Soda paper, I think the previous ones. So I think both of them were Soda paper, but this was a Stack paper that we get for H minor free graph. So they have lots of applications. So for example, you can get a PTAS. Oh, by the way, one other thing. This one, you could, the max cut version that I have mentioned, that could also solve the weighted version. Because everything that I have mentioned was correct for the weighted version as well. If even the edges had the weights, you could say still one of these guys had at most 1 over K weight of opt. And the same thing works. So these are actually, they are very good in handling weights. So PTAS for traveling salesman in weighted H-minor free graphs. This is the paper that we had it. This was solving an open problem of Grohe in 2001. So can we get essentially for this one, we solved this one in the Soda paper. This one, another one is that we can get a fixed parameter algorithm for K-cut and bisection on planar graphs and H-minor free graphs in general. This was solving an open problem of this guy from 2003. So you can get a PTASs using that or fixed parameter algorithm. I will mention how can we get. So there is a PTAS for traveling salesman problem in weighted H-minor free graphs using this theorem. So this was essentially, here we are using again existing bounded treewidth algorithms that was exist there. It was some kind of spanners, and this is the way that we can essentially construct this graph. But these are some of the things that we need to do that. So here we are using the contraction version of them and the edge version. Contraction, we have only edge version. We don't have any vertex version for contraction, because that's edge version is a natural thing. We are contracting edges. So how do we do that? First, we are using the spanner theorem. This spanner actually becomes important later on the problem. What the spanner says that? The spanner says that essentially on these graphs, on H-free graphs, essentially, you can find, so a graph G is given to you. You can find another graph, essentially G prime, which is a subgraph of G. And in this graph, it has two properties. So what is the properties of this? Is that the weight of this graph, so the weight of edges of course, the weight of G prime I will mention means that the weight of G prime, the weight of edges, is at most some constant times opt. And also it contains a 1 plus epsilon approximate solution. Good. So what is a spanner in general? So this is the way that we talk a lot about a spanner. So a spanner, you are given a graph. It is some kind of, I mean, again, a spanner in some sense is, we are doing some kind of sparsification of the graph. So the graph is given to me. I can always find a subgraph of this such that the total weight of it would be at most C times the optimum. At the same time, it has a 1 plus epsilon approximate solution inside. Still, finding that is not that easy. For example, for planar graphs, that's actually very easy. You can, how can you create such a thing? Is this one. For any epsilon, you can do this one. You sort the edges in increasing order, and then add edges one by one. Any edge that you will add, if it helps to essentially decrease the distances between these guys more than 1 plus epsilon factor of the previous distance, then you will add it. So the spanner that we are, for example, here using this one. So you are, again, you are sorting the edges, E1 to EM. You will add the edges one by one. Whenever you are adding, if this edge, by adding this edge, the distance between these guys, it goes by more than 1 plus epsilon down, you will add it. So in some sense, if the edge is necessary, add it. Otherwise, don't add it. This actually would be a spanner that we can use it here. And it is known that it has these two properties. I mean, by construction, it has this property that it has a 1 plus epsilon approximate solution for TSP, because all the distances will be kept within 1 plus factor 1 plus epsilon. And you can show that the total weight of these edges also would be at most, I don't know, C times the cost of the spanning tree, a minimum spanning tree. And the minimum spanning tree is a lower bound for TSP, so it has the bound that we want. So this is the spanner. Good. After the spanner, now we are, so and we know two things. First, we can find the spanner. And again, the spanner is also, it is a H-free graph. The spanner would be a spanning H-free graph, because as I mentioned, it is a subgraph. This G prime is a subgraph of G. So what is the most important things about a spanner? This is the most important fact about it. First, it has a solution, 1 plus epsilon solution. It has a good solution inside it. The other one is the total weight of the edges is at most C times up. While the original graph, the weight of the original graph might be much more than the optimum. Good. Now use this contraction theorem. Contraction theorem is that, okay, so you want to find the TSB? Yes. Okay, just partition the vertices into K-sets, such that if we contract any of them, then the graph has bounded trips. Good. Now, because we are doing all of this, not on the original graph, but on the spanner graph. So in the spanner graph, you know that one of these guys, you will just again. So here, here, epsilon would be actually 1 over, so K. Actually, this is, I think, probably C times K, but I will mention, you will see what is that. So we will partition these vertices into KC. Yeah, I think that would be. So you will partition it into KC components. And for now, C is equal to 1, then we will talk about it. But this is not. So you will partition it into K sets. Now, you know that one of these sets has at most 1 over K of opt. Correct? We are assuming C is equal to 1. This you couldn't say for the original graph. If I do this one for the original graph, I cannot say that it has contained 1 over K times opt. But because this graph that I have it, this spanner, has the weight proportional constant times opt, then I can have this. And here, actually, the correct thing is that I should not, if it is C is not equal to 1, I should get it K prime, which is equal to essentially C times 1 over epsilon. But this is the correct thing that I should get it. So in some sense, the number of things that you are partitioning, why? Because you want to cancel this factor C as well. So you just, instead of partitioning into K parts, you will partition it into essentially 1 over epsilon times C part. Then this C will cancel out. Then you have, you know that like in one of these guys, the size of the edges in this one that are falling in this one is at most, say, epsilon opt. Good. So you know that in one of them is epsilon opt. Good. Now, why are we using the contraction theorem? Why can't we use the, okay, so then what do we do here? We find this epsilon opt, we will contract it. Then we have a bounded Treewidth graph. On that one, we solve the TSB, weighted TSB in polynomial time. This is the issue. Here, we need to use the contraction theorem. If you don't use the contraction theorem, then these edges that you have deleted, so what was the thing? So you want to, here, you want to make sure that essentially you are going through all vertices of the graph. This is a TSB. You want to find the tour that goes through all vertices of the graph. If you delete the edges, then you cannot actually reconstruct. You cannot do this essentially reconstruction. You found something for the bounded Treewidth graph, but there are some edges there. And yeah, the whole thing might be not even connected. That's the problem. But when you do the contraction, you know that the whole graph is connected. Good. So then when you do this, you know that, so in some sense, you went through the whole graph. But this is actually another definition of H-free graph, which is important. So we can say that, so you can, if the graph G has a minor H, what's the meaning of that? It means that for each of these vertices of H, you can find a set of vertices which are connected in G. So if you have, for example, this one, if this is H, then you can find for each of these 4 vertices a subset of these vertices here, such that each of them are connected And then between any two vertices here that there is a vertex, there is an edge between them. There should be at least one edge between these two vertices, two of these vertices. These definitions are equivalent. So if this graph G has the H as a minor, it means that for each of these vertices of H, I can find a subgraph of this. Again, these are disjoint. Each of them is connected. And then any two vertices that they have an edge here, the corresponding subgraph, they should have one edge between them. If we have it, then we can contract it. Why? Because if these guys are connected, you can contract the whole thing into one vertex. You can contract the whole thing into one vertex. You can contract the whole thing in this vertex and delete everything else. Then you will get this H as a minor. Good. So why did I mention here this? Because of this. Now here, so in some sense, I can say that for each vertex here, there is a super vertex here. So for every vertex H, I have a super vertex in G that is corresponding to H. Now, okay, so the same thing here. So here I have contracted. So I have contracted some edges, and then I have created a TSP. But this is the issue that these vertices that I'm working with them, some of them are super vertices. It means that inside them, if you open them, there is actually a tree. Because I contracted them to such that I get this vertex. So this is the same story that I have mentioned here. So this vertex is a super vertex. This super vertex, I need to open it to get a TSP for the original graph. So because this is, so I know that when I open this vertex, then it has a subtree inside. So these are the original vertices. This was the super vertex. These are the original vertices. Good. Now, what is the idea? The idea is that now that I have this, so I will open it now. I will consider each. So I created something on this contracted graph. So this is a contracted graph. For this contracted graph, I have just find some TSP. But then I will, each of these vertices, it may have some super vertices. I will open it up. And I know that there is a tree there. And now what can I do? Essentially, this part is not that different from the TSP. I can say that this, when I open these ones, I can add. So what do I need to do that? Here, when it's a TSP, if you see this TSP, actually is already an Eulerian graph. Because from each vertex it's coming and it is going. Good. So it is already an Eulerian graph. And it's connected, the whole thing. So I need to open up these guys and make sure that the whole graph is still Eulerian. Then there is a TSP tour and I'm fine. How do I open it up? I will open it up this one. I will add, essentially double the edges of the spanning trees there because each of them is connected. I can add twice the set of vertices there. I may add, the only issue that now some vertices have essentially, some vertices may have an odd degree. For them, I can add always a perfect matching. And this perfect matching is at most, you can say, half of the spanning tree, or say even the size of the spanning tree, such that I will make the whole thing's Eulerian. So each of these guys, essentially, I can make it Eulerian. How much do I pay? I will pay, maybe 3 times the set of edges here. But I knew that the total set of edges here was epsilon opt. So 3 times epsilon would be epsilon prime. So I found essentially the original things here. I will pay 3 times opt here. And again, this 3 you can actually eat it in this factor. So instead of, again, do it k times epsilon, do it, for example, 3 times c times 1 over epsilon. You just make the number of these, because that's up to me. So I will just do that. And then I will solve this problem in that. Then I will open it up. I will make the whole thing Eulerian, and then I will find the Eulerian thing. And this is the total thing that I will pay more would be 3 times epsilon. And oh, one other thing is also important. When this is also important. When I make this contraction, I will make this edges 0, correct? I need to do that. If I delete edges, it means that I will make some of these edges infinity, the connection between these two guys. When I do contractions, the edges become 0. It means that in this bounded Treewidth graph that I obtained, the solution would be at most optimal. So if I delete it, I essentially lost the connectivity of this graph. I couldn't say that the optimum solution that I found on this bounded Treewidth graph is bounded by the actual line. But when I do it essentially in this way, I will contract it, I will make it 0. If you make the edges 0, the TSP will not go up. But if you make the edges, cut some of the edges, the TSP can blow up. So TSP is contraction close, not minor close. Does it make sense, the whole thing? So this is like, you see, this is like the meta theorems that now we are talking about. This, like this one, you are doing that, and then you will do it, and then you can get this result. That was the open things because this theorem was not there. Now that you have this theorem, you could solve this one easily. So, and this was actually, the people worked a lot on this thing. So these are like some of the original things. This was a very important result, PTAS for unweighted planar graph, 1995 by Christos and others. Christos Papadimitriou. Then there was Aurora that they had a PTAS for weighted planar graphs. Then there was a PTAS essentially for like essentially linear PTAS, like the running time was better. Then there was a Q PTAS for this graph, and at the end we could get it for weighted H-minor free graph using this meta theorem. And then everything is clean. You just use this theorem. The rest is like very not that hard. And so you can also generalize. For example, you can say that instead of PTAS, you can find the minimum weight CH connected H-minor free graphs. That also you can get it. This is like essentially instead of, you can get a CH connected graph, means that between any two vertices, there are disjoint paths between them. This is generalized. This one. Another thing I want to say for fixed parameter algorithm for K-cut. But anyway, one other thing. So this is one thing that I mentioned. When you contract, so I mentioned you can make it into K pieces. One other important thing that we know that when you delete any of them, all of them is saying that the Treewidth of them would be C times K. So it would be linear in K. The Treewidth of these things is actually linear in K. And that's somehow the best case that happens. So for any large K, so this is the idea. So if you want to get a better PTAS, you just divide it into more pieces. The problem is that when you make it there, then the Treewidth of this graph, when you delete one, would be C times K for some constant C. But it goes linearly in K. It means that the Treewidth of the graph becomes larger. And generally, as I mentioned, the running time of this algorithm would be 2 to the Treewidth. So it means that the running time will go up essentially. It would be 2 to the order K essentially. And this K, as I mentioned, is 1 to the epsilon. So the running time would be to the 1 over epsilon times n for this getting PTASs. So you want to get better epsilon, a smaller epsilon. Yes, you can do it, but the only issue is that the running time also goes exponentially down with 2 to the 1. Now this one. So what is the K cut? So you want to remove the fewest edges to make at least K connected components. Fewest edges such that you will make at least K connected components. So can get a fixed parameter algorithm in H-minor free graphs. How come? So this is the important thing. Average degree, we discussed the average degree of planar graph is at most 5. In general, average degree of H-minor free graphs is size of H times a square root of log of H. For a constant H, it would be constant. So, you know that, as I mentioned, so the C of H, the average degree would be C of H, which is size of H. This H means essentially V of H. That's the meaning of H. So size of the vertex set times the square root of log of the size of the vertex set. But it's a constant as long as H is we generally consider H-minor free graph where H is a constant. So everything would be constant. So we know that the optimum would be at most CH times K. Good. So in H-minor free graphs, we know that if there is a K-cut, so what is the idea for fixed parameter algorithm? We want to say that if there is a K-cut in the graph, I want to find it in fixed parameter times this K-cut. So if there is a K-cut in the graph, I know that, because the average degree of this H-minor free graph is at most constant, optimum would be at most CH times K for an H-minor free graph. Why? Because you want to make it into K-connected components, correct? So you know that the average degree is at most K, is at most C of H. So what do? So you will consider one vertex. So consider one vertex at the time and cut all the, consider the vertex of minimum degree and cut all the edges there. So if you do K of this cut, you will pay at most C of H times K and you have K connected. Actually, if you do K minus one of them, you will get that. So K is given to us. I want to say what is essentially the optimum solution for this K cut. So I know that for any H-minor free graph, the optimum would be at most CH times K. Correct? So what's the meaning of that? It means that I will do a contraction decomposition with C of H times K plus 1. So I know that optimum would be CH K plus 1, CHK at most. I will divide it into how many sets? CHK plus 1. What is the idea? The idea is that I know that optimum in one of these things that I have it has no edges. Good. So I will partition this one into CHK plus 1. Optimum by, essentially pigeonhole principle. In one of these sets does not have any edges. What's the meaning of that it does not have any edges? It means that optimum does not cut any vertex, within this set. It means that optimum actually keeps the connectivity of this set. That is corresponding to the fact that we can contract this set essentially. Because we cannot use deletion version. We need to use contraction version here again. We know that you can contract this edge set into one thing. So optimum does not cut it. So we are fine to, optimum does not cut anything. So it means that it is fine for us to contract it into one vertex. Or like contract all these edges because optimum does not cut it. No, we will contract it, then we have a bounded Treewidth graph. We will solve it. So the running time would be 2 to the order essentially O tilde K plus N. So this is the first result that for K cut, for any K, there is essentially, you can solve the problem on H-binary free graph with this running time, 2 to the order K, N plus N to the order 1. This later has been generalized to arbitrary graph. For arbitrary graph also we can get this. See, that is more complicated. But this one is a very easy consequence of that. Again, you just know some bound on the optimum, which would be at most CH times K. Take the number of layers, one more than that. You know that in one of them, we don't cut any edges. We don't cut any of these edges. So it means that it is safe for me to contract. But when I contract it, then I have a bounded Treewidth graph. And the solution would be essentially the solution of opt. And this would be exact. because we are not losing anything here. There's no approximation. Just the running time becomes this one. Why? Because when this is the case, to solve this problem, the running time of this would be 2 to the CHK, which is, this is to solve it on bounded Treewidth graph, which is essentially 2 to the K times. Good. So let me just, finish this one by giving some ideas. All of these theorems actually can be obtained from these things. So the first thing that I wanted to mention is that, how can we obtain these 3 theorems that I mentioned? So the H set or vertex set can be deleted into K sets, or the H set can be partitioned into K sets. All of them comes essentially from this. The idea is that you are taking the BFS tree. This BFS tree, you will do it. This is in planar graph. For H-minor graph, bounded tree it becomes harder. But generally, either you will get either you do the BFS tree on the graph itself, on the planar graph itself, or in dual. If you do it in the dual, you get contraction theorem. If you do it in the actual graph, you will get the deletion version. And then you will just do BFS on this graph. How do you do that? Then for any K, you will cut this. So this is the BFS thing. So if K is equal to 2, for example, you will, this is the thing that you want to delete. You will delete this one. Then you will do it essentially this one, then this guys, and then this guys. Every other layer, you will cut it. These are the vertex set. If you want to do the edge set, you will cut these edges, then these edges. So, so these edges, and so on. So essentially, you will. This is one of them. So then you can actually. So this would be the way that you are cutting these things. You for any. So yeah, so these are the set of things essentially that you are cutting to get this result. In general, you will cut all those layers which are R mod K. So that's the idea essentially, that you will cut it and you will get these things. So you will say if you cut this one, then each of them have a bounded Treewidth essentially. And so these are the different layers. So essentially, you will for each R mod, so you will partition the vertex set into different vertex set or edge set into these R sets, such that if you delete any of them, and these are all edges or vertices that are R mod K for any R. Now, if any of these are, you can partition them. If you cut any of these guys, then you have a bounded Treewidth. If you do it in the dual, you will get the contraction theorem. And finally, this is the main thing essentially that we are doing. For all of this theorem, when we want to go for H-minor free graphs, this is the thing. So it said that any H-minor, this is essentially graph minor theorem. It said that any H-minor free graphs, it is a tree of almost embeddable graphs. So so essentially, any H-minor free graph, this is the whole thing that is Robertson and Seymour they proved. So that any H-minor free graph, you can represent it as some kind of trees. So it is somehow generalization of Treewidth graphs actually, bounded Treewidth graph, H-minor free graph. Is that you can represent these whole things as some kind of trees of this almost embeddable. What are the almost embeddable? Almost embeddable, you want to get it. It is some kind of bounded genus graphs plus some apices, but the number of them. So the genus here is bounded. The genus is bounded. So it is somehow planar graph, not quite planar graph bounded genus. Then you have bonded apices. Apices are those vertices which are outside of this surface. So we can have some apices that they can be connected to any vertex. These apices are free, but their number is bonded. There are also have some areas which are non-planar, but they have bonded path widths, which is essentially means bonded Treewidths as well. So you have essentially a few areas that these are also are non-planar and they have bonded path widths. So, good. So this is, I want to just finish this one for these things again. So the idea is that if you want to get these layers, you just essentially do a BFS and you will cut it according to this R mod K. These are the way that you can get it. If you do it in the dual of the graph, you get the contraction. This is for planar graph. For H-minor free graph, you need to use this theorem. This theorem says that essentially any H-minor free graph, you can represent it as a tree, but this tree essentially is some kind of tree decomposition. But each of them in the tree decomposition, you have a bonded number of vertices. Here it is not the case. You have an actual big graph. This big graph is not even planar, it's more general than planar. It's a bonded genus graph. It may have K vertices, these are called apices, apex vertices. K apex vertices, but the number of them is bonded. You have some areas of non-polarity, but these areas, they have bonded path widths. And again, it means that bonded Treewidths. So anyhow, it is complicated, but you can deal with it to prove all these theorems, such that you can generalize this from planar graph. First, the idea is that you will generalize it from planar graphs to bonded genus graphs. Then in the bonded genus graph, you need to also generalize it to apex graph when you have some apices, and then you can possibly generalize it for H-minus graphs. So we are using that 500 theorems here essentially to prove this. But for planar graph, as I mentioned, these layers, everything can be obtained either in the graph or its dual by just some simple BFS. And that's it. So I think that finishes this one and this meta theorems that you can use it and you can get it. So almost anything that you want to get on planar graph or H-minor free graph so far, you can use one of these theorems essentially to get the result. If the result is this. I stop here.